Hello, dear students. Welcome to session number 9 in the course Math 204 offered to Business Informatics students, semester 2. I hope you are feeling well and that you have studied the past sessions. And as we said, if you have any question, you may refer to me as soon as possible into our studying group on Facebook, Math 2 space S20. In this session, we are going to discuss the diagonalization or the diagonalizing of a matrix. Here, if you remember, we said that the diagonal matrix is any matrix, I can write here, is any matrix of that form, where we have elements in the diagonal, in the main diagonal elements, and zeros elsewhere. So in general, A is a diagonal matrix when all Aij, the elements are equal to 0 if I is not equal to j. If they were off-diagonal elements, I is not the same of j, but for A11, no, there is a value, it's non-zero. For A22, it's non-zero, there is a value, and hence we call this a diagonal matrix. Today's topic is discussing when we have a squared matrix for a n by n to be diagonalizable. It's diagonalizable if it has distinct eigenvalues. So I will say if and only if A has distinct, which means different lambdas, because we were simplifying the eigenvalue always with the word lambda. This diagonal matrix, if we're able to diagonalize any matrix A and write it in a diagonal form, this diagonal form is very beneficial. It's very smooth to deal with in different operations, because many calculus operations and numerical operations in the numerical analysis deal with or transform the operations into matrices. And dealing with special kind of matrices, such as diagonal matrices, makes the problem very flexible and be able to add operations up to it. For example, let's say that we need to commute a to the power of any power, for example, to the power of n. Make it in general. Raise a to any power. If this a is that one in that example, in that case, we will only raise the diagonal elements. 1 to the power of n, it's 1. And then 0 and 1 over 2 to the power of n. First, it's half to the power of n, and then distribute the power in the numerator and denominator. So any power of a can be deduced by only applying this power to this diagonal elements. This is a beneficial of a very good benefit of using the diagonal matrices. Let's see here. Now, if A is diagonalizable, and we will say that it means that, or how we will know that definitely A is diagonalizable, as you have discussed in the lecture, there is a theorem which states that A is diagonalizable if and only if A has distinct eigenvalues. So we might try to get the eigenvalues of a matrix, and then we will have a D matrix, a diagonal matrix of that A, which will hold its eigenvalues. If we are dealing with 3 by 3 system, the A was 3 by 3, so we will have a diagonal matrix of the same dimension with elements only in its main diagonal elements. So see, these will be the only values, the only non-zero values, which are the eigenvalues. And this matrix A, if it's diagonalizable, it will have as well another matrix, which is called capital P, which will hold the eigenvectors corresponding to these eigenvalues. So we have the eigenvector here, the 3. They are, n is equal to 3, so every vector belongs to R3. And hence, for any diagonalizable matrix A, we can know this if the A has distinct different real eigenvalues, and we will set this diagonal matrix in that format, and it will have as well an invertible matrix of its eigenvectors, such that these eigenvectors are as well, it was noticed that they were linearly independent. So we know now that this matrix has distinct eigenvalues and linearly independent eigenvectors. And this is an important characteristic. Let's move to exercise 1 in worksheet classwork 9. In exercise 1, it says determine whether these matrices, I've picked this matrix of them, are diagonalizable, whether they are diagonalizable or not. And we will see that the matrix can be diagonalized or it can't be. The condition of being diagonalizable is to have distinct lambdas. So what we are going to do here, exactly we are going to try to get its eigenvalues and observe if they were different, then it will be diagonalizable, and we can get this D matrix and as well format that P1. Let's get the eigenvalues like we did in the last session. We will solve for the characteristic equation, which states that this A1 minus lambda times I of the same dimension, which is 2 here, get the determinant equal to 0, and hence only the diagonal elements will be changed. They will be 13 minus lambda. The off-diagonal elements will be the same. Here we will have negative 12 minus lambda. Get the determinant equals 0, and we can get it using the Saris rule or the cofactors like we did before. We multiply the diagonal elements to have 13 minus lambda multiplied by negative 12 minus lambda minus this product, which is negative 10, so we can write it directly 150 equal to 0. It seems that we are going to have a polynomial of degree 2, and it makes sense because we are dealing with a 2 by 2 matrix. And let's see the two eigenvalues. We will have lambda 1, factorize, of course, using algebraic or factorization or using the calculator. Now we have two distinct or different eigenvalues, which means that this A has a diagonalized matrix D, which holds these two eigenvalues, negative 2 and 3, in the diagonals. So our answer to the first part of the question is yes, it's diagonalizable, and here is its diagonalized matrix. Now, if they are diagonalizable, find P. P is the matrix which include the eigenvectors. So let's work for the eigenvectors. Moving this part in the middle. The eigenvectors, if you remember, we are dealing with the same matrix as coefficient matrix to the unknown x equal to 0, and we solve for this homogeneous system. Now for lambda 1, which is what it was, negative 2. So we will have here plus 2 in the diagonals of a 2 by 2 matrix. Dealing with this A, so it's we can write it directly. It's 3, negative 10, 15, negative 12, and this will be added to 2, if you can't imagine it, and then we will have 13 plus 2, this is 15, negative 10, 15, negative 10 as well, plus 2, and of zeros, what are we going to do next? Yes, use the elementary row operations in order to reduce this matrix and reach its echelon form. Use the elementary row operations, and we can divide by 15 here or directly subtract, and hence we will get the 1, negative 2 over 3, and zeros. We said that this homogeneous linear system of equations, it has only two possible solutions, which is the trivial and non-trivial. Here we have the infinite number of solutions with the second parameter is free. The first one has a pivot, so it's fundamental. The second unknown is its corresponding diagonal element is 0, which means it's a free parameter. And we can say that x2, we may assume that it's equal to t, where t is the element of all real numbers, and then write x1 in terms of this t. Or, like we did before, we may leave x2 with its dummy name. It's senseless to call it x2 or t or whatever. And x1 is equal to, move this to the other side, 2 over 3 multiplied by x2. So the vector that we are looking for here, we have called it x, this eigenvector. The first element got to be of 2 over 3 x2, and the second one is x2. So this is the eigenvector for that corresponds to this eigenvalue, negative 2, right? And we know that the eigenvector actually is an element of the span set of this vector, which is the multiple of this vector. Let's seek the other eigenvector that corresponds to the other eigenvalue, which is here equal to 3. We will repeat again our procedure, but this time for lambda 2, which is equal to 3. So we will solve a1, this a1, minus lambda I2, and this lambda directly we can write it at that time, it's 3, and we will solve of 0. We will set this augmented matrix, and hence we will find, using the elementary row operations, we can find the reduced form of the matrix in that format, which means that x1 has to be equal to x2, right? We have here x2 is a free parameter. So we will keep it as it is, and therefore the vector is this vector here. We didn't call it yet. I don't want to call it x2 because we have already used this x2, so let it be here v. So this v is 1 and 1. Or you can write it first that x1 and x2, which is equal to x1. So you may write it first x1 and x1. Why? Because x1 is x1, or it's t. Okay, and x2 is x1 as well, or the same t. And then take this dummy name as a common factor, you will find this vector 1 and 1. And therefore, the P matrix that we were looking for is composed of these two eigenvectors. This is the second one, and that was the first one. And please pay attention to the order. In the diagonalized matrix here, we stated lambda 1 first and then lambda 2. So we will take the first eigenvalue corresponding to this first lambda first as the first column, and the second one as the second column. This is a newly introduced matrix now for us. It's called the capital P matrix. It's the matrix of eigenvectors. And it holds the characteristic that A can be written as B inverse. we can write it as B times the diagonal matrix. We can rewrite A in terms of its diagonalized matrix and its P matrix, which is always invertible. Here, A and D are called similar matrices as well, because they have the same eigenvalue and they have, by the way, the same rank and the same determinant value. They are two similar matrices. And we can rewrite A in terms of its diagonal matrix and eigenvectors matrix. And the benefit of rewriting a matrix using this formula is that we will be able to commute something like this, a to the power of 6. If we need to get a to the power of 6, okay, let me write it again. Here, a to the power of 6. Let me first show you if we are going to double this value or raise it, square it. Squaring this value, if we need to get a to the power of 2, what is that? It will be this formula, b, d, b inverse, multiplied by the same formula, b, d, b inverse, right? What do you know about multiplying a matrix with its inverse? This gives us the identity matrix, right? And then we have the P, D times identity matrix times D again, and then B inverse, right? Identity matrix, which is the one of matrices, multiplying it by any matrix is, it keeps the entity of the matrix. So it will get us the same D. We can remove it. Here it's D times D. So it's D what? D squared, right? It's D squared multiplied by the last term here, which is the inverse of B. So A squared, sorry, I wanted this bar in the middle. So it's A squared equals to B times this diagonal matrix squared times B inverse. So any power or exponent we need to evaluate it or commute it for our matrix, if it's diagonalizable, we will just apply this power to the diagonalized matrix. As we have stated before, if the matrix is diagonalized, so there is only non-zero values in its diagonal elements, positions, any power will be raised only to these values. So now getting a to the power of 6 is what? It will be B, but first we need to get the inverse of B. We have discussed how to find the inverse using the Gauss-Jordan technique. For the 2x2 matrix, I can teach you a small trick that maybe some of you already know it. If we need to get the B inverse for B, if it's 2x2, there is another technique which is called the cofactors, but we didn't discuss it. We can simply get it. It's 1 over the determinant of B times another matrix. We will exchange the diagonal elements, and so we will have 1 and 2 over 3, and multiply the off diagonals by 0. What we did here, we have exchanged these two elements, and we multiplied the off-diagonal elements by 0. This is applied only for the 2x2 matrix, okay? You cannot apply it for the 3x3. You have to get the inverse using the Gauss elimination technique that we have already discussed, okay? So the cofactors, we can do it with the 2x2 to save our time, but don't forget to multiply outside with the 1 over the determinant of B. What's the determinant of B here? It's 2 over 3 minus 1, so it's negative 1 over 3. So we have the B inverse as negative 3, 3, 3, and negative 2. Because this will be 1 over 3, which means it will be 3 and negative 3, so it will get this inverse matrix, and back to our A diagonalized matrix. Therefore, A to the power of 6, that one, is equal to P, this nice matrix, and then multiplied by D raised to the power, the D where we're having lambda of -2 and 3, right? And we wrote it in the same order, so it's -2 power 6 and 3 power 6. We have zeros in the off-diagonal elements, and finally multiplied by B inverse, which was the red one here. Apply the power of 6 to these two elements and then do the multiplication. If you want to verify, sometimes you can find this as a question. If you need to verify that this will be equivalent to A to the power of 6, I will give you the final answer. If you want to double check, it will be 2059 negative 1330 and 1995. And the negative 1266. And here, this is A to the power of 6. Now what we have did, the question asked to determine whether the matrix is diagonalizable or not, and we knew this after getting its eigenvalues. We are able to decide that yes, it's diagonalized because we got two different eigenvalues, and hence we constructed the diagonalized matrix of this matrix A, and after which we, if it was diagonalizable, and that was the case, find its P, and that P matrix is the matrix of the corresponding eigenvectors, which we have deduced, and then we could format this different format of A. We can rewrite A in terms of its diagonalized matrix and eigenvectors matrix in this format, and then we can get many benefits. One of it is getting or commuting different powers of A directly using its diagonalized matrix. So we applied the power to the diagonalized matrix and apply this product or this multiplication. Of course, take care of the order, and hence you have got the A raised to the power of 6 instead of multiplying how many matrices. If we didn't use this diagonalized matrix, we would have multiplied A by itself 6 times. So of course, this is a great benefit. If it was only for it, it was enough. Okay. Let's work with a different matrix. This is part B. Again, we want to know whether it's diagonalizable or not. And as we agreed, if it's diagonalizable, it will have different values of lambdas. Okay. So to answer the question if it's diagonalizable or not, we have to find its eigenvalues. This is the easiest way, let's say, to know it. So we will solve A minus lambda I raised to 2. The determinant is equal to 0. This will change only the diagonal elements, which will be 2 minus lambda, 1, negative 1, 4 minus lambda. Find the determinant, which is equal to 0. Get the determinant by the preferred technique. You will find a second degree polynomial. Minus negative, it will be plus 1. equals 0. Without equals 0, here it's the characteristic polynomial. Now it's the characteristic equation, so you have to memorize it, their name, if you are asked for deducing it, so you know it. And then solving this values, now we will find that lambda 1 is equal to lambda 2 is equal to 3. So here we have two identical eigenvalues. Can you figure out the diagonalized matrix? After getting the eigenvalues, we can decide whether it's diagonalizable or not. Of course, it's not diagonalizable. So we will say it's not. The matrix A2 is not diagonalizable, since we have, because of multiplicity, you can write it like this, or because we have the same eigenvalue. Okay. We can find the corresponding eigenvectors, yes, of course, but it's of no use. So as I told you, the matrix can have distinct eigenvalues and be diagonalizable, like the previous example where we were able to rewrite the matrix in its diagonalized, in terms of its diagonalized matrix, or it can be not able to be diagonalized, and hence we have to deal with it as it is, or it doesn't have this characteristic property. Let's do this example to another matrix. So here we are given a 3 by 3 matrix. So n is equal to 3. What does that tell us? Now we are expecting 3 distinct eigenvalues if this A4 was diagonalizable, and their corresponding 3 eigenvectors that belongs, all of them, to R3 to format the P matrix and be able to rewrite it. If we here solving this characteristic equation, a to the power of 4 minus lambda I wait a minute. Solving this characteristic equation and try to find the eigenvalues, we will find that lambda 1 is equal to 3, lambda 2 is equal to -1, and lambda 3 is equal to 2, which means that we have 3 different eigenvalues. Now let's go for the first eigenvalue and deduce its corresponding eigenvector. For lambda 1 equals 3, we will solve A4, this was the origin matrix, minus 3 times the identity equals 0. Here is the matrix minus 3 multiplied by the identity, and the result is that matrix. We will solve the system as a homogeneous linear system of equations using Gauss elimination, and this is the final reduced matrix in its echelon form, which means that we must satisfy that x3 is equal to 0, right? And that x2 is equal to 0 as well. x1, the first pivot is 0, which means that it's not fundamental, or it's not a basic variable for the system. Therefore, we can assume it by T or anything. So here, the element in the diagonal was 0. So the first unknown will be assumed by T. And then here we have x3 is equal to 0. This is stated. Equation 1 as well. Here we don't have an assumption. If you went directly to this row and tried to assume that x3 is equal to T, you will go then to row 2. You will find that it tells you that x3 is equal to 0. So here x3 is restricted. This will override that thing. So what you read here in row 3, if you directly write that it's equal to T, such that T is element of all real numbers, moving to row 2, you will find that it tells you that x3 is equal to 0. This is restricting x3 or giving it, assigning it a definite value. So T doesn't belong to all real number. No, it's only 0 for that system. So it will override this. Okay, and we will have x3 is equal to 0. And go to row 1, you will read it as x2 is equal to 0. Here all are eliminated. So what is the left unknown? It's x1. This one which we will assign it the T, such that T is element of all real numbers. And hence we will have T as x1 and x2, x3 are zeros. Take T as a common factor or keep its dummy simple as x1, and hence we know that this x belongs to the span set of this vector. Now go to lambda 2. We were having here, we had 3 eigenvalues, so we will do the same steps in order to find the other 2 eigenvectors. Let me close this window. And here we have the diagonal matrix with the 3 different eigenvalues and the P matrix, the invertible P matrix with the 3 deduced commuted eigenvectors. And to diagonalize A4, we can rewrite it after getting the inverse of the P matrix as P times the diagonal matrix D, which is the matrix of eigenvalues, times P inverse. Apply the multiplication, the row with the column, and then keep the row with the second column to get the element in row 1, column 2, and then row 1, column 3 will be a dot product between column 1 and row 3, as we have discussed it several times before, and you will get that, you will get A as it is. Now, if you want to raise A to any power, you can do this. Let me tell you something before we finish this session. We have stated that we can rewrite A in terms of its P and D matrices, and in this case A and D are similar matrices, which is denoted by A and this simple into D, and in that case they will carry the same rank value, the same determinant, therefore determinant of A is the same as determinant of B. This is number 1. The second information is that the rank of A is the same as the rank of B. Number 3, A is invertible. Here we said that A and D are similar. So A will be invertible if D is invertible as well. And if D is invertible, then A is invertible. And they have the same eigenvalues, A and D. Also, we know that this relation holds, this one, and it has some consequent. If you multiply here from this right-hand side with P and the other side with the same P, this is an applicable operation, right? Then we did nothing to the ratio. P times P inverse will turn to I, and this I will get into D because I times D is D, right? If I wrote it here, P from the right-hand side, so you will have P times the rest of the right-hand side, and multiply B from the same side with A. Okay. With a different color. So we have here times B, and this product turns to the identity. Identity times D is D, and hence we get that AB is equal to BD. This is a different format for writing this condition. Another format, if we want to deduce it, we can multiply by B inverse from where? From the left-hand side. And hence we will get the same AP, but multiply with B inverse from the left-hand side, which is that one. B times B inverse is identity. Identity times D, then it's D. So D as well is equal to B inverse A times B, and this is another equivalent term to this one. So these three formats are identical. If you want to show that a matrix is similar to another matrix. That was for this session. Please stay safe and study well. See you in the next session. Until then, goodbye.